All right, taking a look at the diver problem. It says we've got this 62 kilogram diver, and she starts off on a diving platform 12 meters above the water. She's going to step off the platform and fall. When she does, it says when she hits the water is going to push up against her, slowing her down with an average force of 1,790 newtons. They're going to ask us to solve a few things about energy types. At the very end, the final question is going to be about how deep under the surface of the water she goes before she comes to a stop and then bob back up. So take a look at this. I'm going to start with a sketch, right? And so I'm going to say, all right, we've got that diving platform, that diving board, and then we have the pool. Here. Put some water in there. All right. Let's see here. They tell us later on. They kind of indicate that she's not going to be like jumping up in the air or anything. She's essentially going to kind of step off the diving board and kind of fall to the water. Sploosh. Okay. And then she would go some distance down, some depth down in the water before coming to a stop. All right. Let's see here. They tell us that her mass is 62 kilograms. From where she steps off down to the surface of the water, they're telling us it's 12 meters. All right. And then once she's in the water, here, she's continuing on down here. That water pushes against her motion, pushes against her with the force of the water. That's 1,790 newtons. There we go. All right. So let's take a look at the first thing they want. The first thing they want us to do is construct LOL diagrams for the instance when she has just stepped off the platform, when she's halfway down to the water, just before she contacts the water, and then when she's at the maximum depth. So I'm going to mark those files and tag them. So position A, halfway down to the water here. Position B, just before she enters the water, and then when she's at her maximum depth. A, B, C, D. All right. So first thing we want is LOL diagrams for those positions. So oftentimes when we do LOL diagrams, we'll do like the L's, the energy bar graphs for the different positions, and then we'll just do one big O, one big energy transfer diagram for the whole thing. But I'm going to kind of go crazy with this one and do transfer diagrams between every step. So we're going to kind of show everything here. So first, just go ahead. L, O, L, O, L, O, L. There we go. We're doing this for positions A and B and C and D, and the transitions between C and D, B and C, A and B. All right. The next step then is to choose our system. Okay, and part of choosing the system is going to be thinking about what forces, outside forces, act on it and how they interact with it. So I usually do a force diagram next, and I usually start my system small. So I'm going to start with just the diver, right, and think about the forces they're acting, and do I want to expand my system? So while the diver is falling here, what forces will be acting on the diver? And you'd say, well, just gravity, right? Well, while they're in the air, it's just that gravitational force. Once they get in the water, though, there would be two forces. So from position C to position D, the gravitational force and the force from the water. I'll do my force diagram off to the side here because I don't want to clutter the diagram anymore. But yeah, when she's underwater, she'll have gravitational force and that force from the water. I guess I could have drawn that there. Alrighty. So when I go to do my system then, you're like, okay, well, certainly we're going to include the diver in our system. but do we want to include anything else? And so we can see from the force diagrams, the only other things that are interacting are the Earth, so that's that gravitational force on the diagram from the Earth, and the water pressing back up. So do we want to include the Earth in our system? Do we want to include the water in our system? So including the Earth in the system is generally a good idea. We're going to use gravitational potential energy then, and that's kind of the purpose of this problem. Generally, it's almost always going to be nicer to use potential energies when you can, all right? And so I'm going to go ahead and I'm going to expand my system to include the Earth so that I can use gravitational potential energy. I'm going to do that in all of the cases. Now, the question is, the whole way through, my system will be divert Earth. Now, do we want to include the water? Well, certainly there's this force on it from the water. And so if we did that, well, basically at the end, the bottom line is at the end, they want us to solve for that depth that she goes down through the water before she comes to a stop. And so during that, like part of how I'm going to calculate that is going to be through, when they gave me the force from the water, I'm going to figure that out from doing maybe a work calculation, force through a distance for this water. So that's really the only way I have to calculate that. I don't have any information about how the water is going to swirl around and increase thermal energy and wiggles and jiggles because of the impact and because we're moving through the water. I don't have a good way of putting numbers on that. The only way I really have is by thinking about this interaction. And to do a work calculation, it needs to be a force from outside the system. So I'm not going to include the water in the system. That's kind of the logic behind that. I'm just going to keep it at divert Earth. Okay, now that I have that, now we can talk about our transfer diagrams. And so you say, well, transferring, while we're going from A to B, is there an outside force acting on our divert Earth system? Well, now, if the Earth is included, this gravitational force isn't from outside the system anymore, right? Because the Earth is part of the system. And so there's no outside forces, there's no energy transfer. Same thing from B to C, no outside forces, no energy transfer. But from C to D, now there's this outside force, the force from the water. And so is that force pushing with or against the motion? And you say, yeah, we're moving down and that force from the water is up. It's going to be going against the motion, trying to slow the diver down, taking energy out of the system. So I would have a work term here. So I'll draw my arrow going out of the system. This is work done by the water on the divert Earth system, taking energy out. All right. Okay, next, doing the LL diagrams. That's all the energy transfer diagrams done now. We've looked at all the outside forces that could be doing work, so those are done. So now it's time to do the energy bar graphs. And so generally we said, we're just going to go ahead and go through a checklist of our types of energies. And we said we only do include the ones that are changing. So running through the checklist, kinetic energy, is that changing? You say, yeah, kinetic energy is 1/2 mv squared, and we're changing speed as we go down faster, faster, and slower, slower, slower. Kinetic energy is changing throughout the process, so we will include kinetic energy in our analysis. Okay. Next, gravitational potential energy. Are we going to include that? You say, well, is it changing? Well, we're changing heights. Gravitational potential energy is mgh. We're changing h. We'll be changing that, so we need to include ug. And again, we can include ug because we have this gravitational force. It's a force. It wouldn't technically. It's not on the diagram. It's inside the system, acting between the diagram and the Earth. So we can have those ug terms. Okay, what about U elastic? Do we have anything stretchy being crushed or stretched here, returning to its normal strength, normal length? You say no. Do we have chemical potential energy? Any chemical reactions rearranging chemical bonds? And you say no. Thermal. You say generally thermal energy will change if there is collisions or friction. And you say, well, yeah, aren't we colliding with the water? And we go through the water, are we pushing against it and rubbing against it? You say, well, that's all taken care of by this force. That's the interaction with the water. And we're going to do that as a work term here. So we're not going to analyze thermal energy then. We're not including that water. And so we're not going to worry about that thermal energy then. Right? That's the idea there. All right. So this is it. This is it. We're just going to have kinetic energy and gravitational potential energies to worry about in our calculations here. So now, you say, are there any of these values that we know are 0? So we can fill the zeros in. You say, well, start with kinetic energy. Kinetic energy is 1/2 mv squared. So anywhere where the speed is 0, we could say the kinetic energy was 0. You say, well, yeah. At the start here, we're just going to kind of step off and fall. So we're going to say that at the start here, the speed at A is 0. And so we can say the kinetic energy there would be 0. Also, you say, hey, the end point here is when we get to just the bottommost position, which should then bob back up. At that bottommost position, the speed at D is going to be 0, and so the kinetic energy at D is going to be 0. All right, kinetic energy, that's it. So now gravitational potential energy. Is there anywhere we can say the gravitational potential energy is 0? And you say, all right, well, gravitational potential energy is given by the formula mgh. Like, okay, well, that has to do with h, height. Height above where? You got to pick somewhere to call height 0 to make like the reference level for your potential energy. And so usually in problems, we like to pick the lowest position. That way all of our heights are positive. It makes life easier. But maybe that's a little tricky because we don't know what this bottom level is, right? It's some unknown depth here. And that depth, again, is what we're going to try to solve at the end. We're going to try to solve for this. That little delta x distance we go down here. So that's a little tricky. So rather than have a kind of unknown position as our 0 position, which makes figuring everything else out rough, let's go ahead and choose another spot to call the reference level. So I think that most of us would say, well, let's call it like the water line, okay, height 0. So that's at position C then, all right? Call this height 0. If we choose, so I'm going to go ahead and do that for this calculation. We'll go ahead and decide, say here, the height at C is 0. Then the gravitational potential energy at C would be 0. Go ahead and fill that in. Right. And that's all of the zeros that I can mark right now. So at this point, going through an LOL diagram, you say, well, let's go to these other things. Do I know the values for any of these other terms? You say, well, UG, now that I have a height at 0, right? Like I could calculate my gravitational potential energy there. Just use mgh, my height above here. You see, I could get an actual value and plug it in and all that. And do all these calculations and stuff. But the thing is, I don't want the LOL diagrams. The whole point of this exercise isn't to make a really accurate LOL diagram. I want this to be like a guide or something to help us thinking about the problem, to help us setting up the calculations and analyzing, thinking about what energy types are doing what in the problem. So I'm not interested in this being like the super accurate one. I just want to see generally what's happening with the different energy types in the problem. So we're just going to make up a value, right? An obviously incorrect value, but a nice simple value for that starting energy. So those who know me know that I like usually to use a value like 12 is a value I like to use. Because, you know, 12s are divisible by a whole lot of different other values. 2 and 3 and 6, 4. Anyway, so we'll say the starting gravitational potential energy is 12 units. All right? Okay, just picking a value. Okay, now let's take a look as we get to B. Well, can I fill in either of these now? Well, one thing we know, B was defined to be at half the way down to the water line. Well, the water line is 0. This is half the height. As at A, it'll have half the gravitational potential energy. So if it had 12 units here, at B, that will be 6 units of gravitational potential energy. Now, when we went from A to B, was there any energy transferred in or out of the system? No. So the total energy's got to be the same. The total energy here was 12. Total energy here has to be 12. The missing 6 units must be in kinetic. Ta-da! All right, now we'll go from B to C. Okay, when I get to C, all the potential energy is now 0. We're at that reference height. again, from B to C, there was no energy transferred in or out. So the total energy still has to be 12. It must all be in kinetic. Now we go from C to D. In this case, you say at the end, there's no kinetic energy. What energy is left must be in gravitational. You say, but wait, there was some energy that left the system here. Okay, the water did some work pushing against the motion, slowing down the diver, taking energy out of the Earth diver system. So my total energy here is not going to be 12. The energy is leaving the system. My total had better be less than 12. And actually, if the height here at C is 0, the height at D, that's going to be some negative height. We're going to get a gravitational potential energy, mgh. It's got to be less than 0. So multiply by a negative height. So maybe we'll just invent a value. Maybe we'll say, we go down here to say maybe -3, right? Then how much energy was taken up by the water? We started at 12, total units of energy, end up at -3. We must have lost 15. So this took 15 units of energy out of the system. Okay, and that's it. That's my my LOL diagram for this. And again, we chose some of these values were chosen arbitrarily. Our starting value here we just chose, and basically the final potential energy there we kind of chose arbitrarily, but with some guidelines, knowing this had to be negative, and that determined that value. But again, it's just to give us kind of an overall picture and see which energy types we're going to have at which positions and kind of how they compare to each other a little bit. All right? So that's part A. Okay, part B. They ask us, determine the change in the gravitational potential energy from the top of the platform to the top of the water. The change in potential energy from here to here, from A to C. So you say, all right, going from A to C. Okay, we want to know the gravitational potential energy change. You say, well, really, they're just asking us to solve for delta UG, right? You see, that's going to be my UG. Now, I'm going to do like a final minus initial, right? For a delta, right? So you'd say that would be, but you know that we're going to analyze here going from A to C. So at C, that's the final. At A, that's the initial. But later on, we're going to do a calculation from here to here. And so this will be, C will be then the initial, and D will be the final. So when we do problems where we're going between multiple positions and doing energy changes as we go along, it might be kind of awkward sometimes for the energy at one spot to sometimes be the starting and sometimes be the ending. For our notation, it might be awkward. What was the V final at one spot is the V initial at the next. So what I find is, when I do these problems, it's usually nicer, instead of filling it in final minus initial, although that's what we're doing, to just label them, though, as the gravitational potential energy at C minus at A, at the final. So label these variables according to where they occur. So UG at C minus my UG at A. That's the final minus initial. And that just makes it a little bit clearer. And so when I have that value for UG at C, I might be using that as an initial value somewhere else instead of a final. Okay, but anyway, you get the idea. That's just a tip in solving energy problems. Moving on with this, we're trying to find this delta UG. Hey, the UG at C. We define the UG at C to be 0. So that term is just going to whoop, drop out. So it's just minus the UG at A. Can I calculate that? You say, sure, I'll use the formula. That's the mass times the gravitational field strength times the height at A. You say, we know the mass is 62 kilograms. G we know is 9.8, and the height at A, well, we call here height 0, so that's 12 meters up. That's 12, so we know all these values. 62 times 9.8 times 12. And this comes out to be, quick punch in the calculator. And we get 62 times 9.8 times 12. 7,291.2. And our units for energy, right, are going to be joules. So there we go. So this is the change in gravitational potential energy. Our system lost a little over 7,000 joules of energy. You see, well, that makes sense. We are going in the same direction as the gravitational force is pushing. Whenever you go with the direction of the force that's associated with the potential energy function, you lose potential energy. So yeah, that makes sense. So that's part B. Part C. What's the change in kinetic energy from before she leaves the platform to the instant she hits the water? And then what's her velocity of impact? Well, if I set up the big work kinetic energy theorem for this problem, that would look like this. Right? And we're going to set this up again from, they want to know the kinetic energy change from here to here. I say, it's the same situation we're looking at here, but now we're looking at the overall energy equation. Going from A to C, there was no outside force doing work, so there's no work terms. Delta K, we had this, that's what we're trying to find is the delta K. But you say, wait, isn't the delta K and the delta UG, they've got to add up to 0 then, because there's no outside force doing work, there's no other energy changes. And so this value we just solved, that's this. So the delta K must just be positive that much, so they add up to 0. So delta K, we know, has got to balance this out. Delta K has to be positive 7,291.2 joules. Okay, so they add up to 0 here. Okay, so we're figuring that out from this information and this expression. Okay, now they want us to actually find that final speed. Okay, now we already did this calculation here, the delta UG. Let's just do the delta K calculation. And so, jotting this down, delta K, that would be the final kinetic minus the starting kinetic. This is the kinetic at C minus the kinetic at A. And then our delta UG, we already know that's a negative 7,291.2. I'm just going to leave that alone for right now. We'll put our values in a minute. Hey, the kinetic energy at A was 0 because it started from rest. So that term drops out. When I put in my equation for kinetic energy, 1/2 mass, speed squared, this is the speed at C. Hey, that's actually the thing they want us to solve for, the speed at C. So that's handy, right? And then I just have this plus delta UG, which we already found the value for. Do I know the value for the mass? I do, 62 kilograms. I know everything in this line I can solve for VC. If I go ahead and put the values in, 1/2 times 62, VC squared, and then this is a minus 7,291.2. I can solve for VC. So if I do that algebra and punch in the calculator, times 2 divided by 62, take the square root. I'm going to round this off to 15.3 meters per second. And that's my speed. Okay. Do I need to put a negative out here or something? No, for direction because it's going down. You're like, no, they're asking for speed. Velocity has a direction. This is just the speed. Yep. Actually, I guess in the question they asked for the velocity and impact. So I guess I would say, I'm just going to put it like this. I'm going to say it's that downward, okay, to give direction. All right. You could make it negative and make it a velocity if you wanted, but downward. So it has to have a direction for the velocity, right? So I'm just putting it on that way. All right, that's part C, which takes us to part D, the final part where they want to know how far below the surface of the water will the diver go before stopping. We're now trying to find this distance. Okay, this is going to be the tricky part, okay, of this problem. There's a part in here that's kind of tricky, the way we've set this up, and so I want to share that with you. I'm gonna erase my work here so I have some room to do this out. Sorry, because we're going to be analyzing the motion now. Now, we want to know this distance. Most people, when they look at this, the most direct way of solving it would be to calculate from C to D then, right, to find the distance from C to D, right, and do an energy calculation from here to here. it is possible to solve this problem going from another location that we know all the information for, A, and just go from A to D. And you could figure that out too. But I think most people would do this going from C to D, so I'm going to set my solution up that way. So it's similar to what you've probably tried on your own. So here we go. The only value that I'm going to need to remember is this one. Well, I can remember that 7,291.2 joules also. Yeah, so here we go. We'll set this up. So I'm going to do an energy calculation going from C to D. Okay. And of course, our system is still diver at Earth. And so that'll look like this. Sigma W is delta K plus delta UG, the work energy theorem. And you say, all right, going from C to D, do I have any work terms? You say, well, I've got two forces acting on the diver, but the gravitational force is inside the system. And so that's not going to be an outside force doing work. Instead, we're going to take the effects of gravity into account by having a delta UG term on this side. Again, you never want to do both work by gravity and gravitational potential energy in the same equation. You'd be counting gravity's effects twice then. So we don't want to do it one way or the other. Okay, because we're doing our system diving Earth, we're going to have a delta UG. But I will have work term from the water. That force of the water pushing against the motion, it is going to be doing work. So I'll have a work term for that work done by the water. On the right side, delta K. So that'll be my kinetic energy at D minus my kinetic energy at C. And delta UG, the gravitational potential energy at D minus my gravitational potential energy at C. All right. Will some of these terms be zero? And you say, well, sure. At the end, the speed is zero, so the kinetic energy at D is going to be zero. At height C, that height is zero, so the gravitational potential energy at C is zero. So those terms are going to drop out. So this is my work energy theorem showing only the non-zero terms. Okay, and you remember this is something that I expect you to show in pretty much every energy problem. Because it kind of shows you the overall view of what's going on. We're losing the kinetic energy we had. We're going to be at some new gravitational potential energy, and it's because of this, and this work done by the water is going to modify the total energy. So here we go. We're trying to find that distance that we want. So that's going to show up here, right, in that work done by the water. So I'm going to use the work equation. Now, just a reminder, you say, hey, the work equation is F dot delta X, force dotted with the distance. And we do that dot product, that means I'm going to take the absolute value of the force, the cosine of the angle between the force and the distance, and the absolute value of the distance. So the only plus or minus comes from the cosine function, right? So when I do that here, that's going to look like this. The force of the water, absolute values, cosine of the angle. Now, what's the angle between the force of the water and the motion of the diver? You say, well, that's 180 degrees. And then the distance we go, that's this delta x we're trying to find. Okay? All right. On the other side of the equation, now I'm going to have minus my kinetic energy at C. We could punch in the whole formula, minus 1/2 mv at C. But we remember before, we calculated that value already, that's 7,291.2 joules. I'm just going to leave it as a negative Kc for right now because we know the value. I don't need to break it, sub in the form for kinetic energy. Our UG at D, though, that's a value we don't know yet. So let's put in the formula for that one. It'll be mgh, right? Now, what's the height here? Well, it's going to go this delta x here, right? It's going to be the height. And so at this point, you say, hey, do we know the force of the water? Yes. 1,790 newtons. Cosine 180, that's a -1. Delta x, that's the thing we're trying to find, right? Okay, see, we know it's 7,291.2 joules. Mass, we know, is 62. G is 9.8. Delta X, that's the thing we're trying to find. So usually you'd say, okay, at this point, we'll take the variable we're trying to find and we'll like group those terms together and then factor it out, set it by itself, isolate that variable, and then solve, right? But there's something tricky here. And that's that this is an absolute value of delta X. So this is going to be a positive value. But over here, we know this height is negative, actually. And it's going to make this potential energy term negative. It's actually a negative value here. And so these aren't the same thing. Absolute value of delta X and delta X, they're not the same thing. And I want to group them together and factor them out to like solve. So the trick I'm going to use here to be able to have the same thing to factor out and compare is I'm going to make use of the fact that I know this is a negative value. I know that delta X is going to be negative of the absolute value of delta X. Do you see what I'm saying? So if I substitute this in for delta X, I'll have the same thing now, absolute value of delta X that I'm solving for on both sides. Make sense? So it's the same variable. These aren't really the same variable. This variable and its absolute value. Okay, so that's the tricky part here. Okay, this is to me the part that's strange in this setup of the problem. So to make that substitution, so now we can put our values in. My force of the water, 1,790 times cosine 180 is just going to be a -1. Delta X, as the value is what we're trying to find. I don't know why I'm putting the values in. I probably should have rearranged. The whole point was that it's okay. -7,000. Was that 7,190.2? I think that was the value we got. And then plus mass. Now, when I substitute this in, that's going to give me a negative from that negative delta X. That negative is going to make this term negative. Here's my mg, 62 times 9.8. And then that delta X I replace with that absolute value delta X. There we go. So now I have the same variable there, absolute value delta X. I can like factor it out and solve and all that jazz. Okay, does that make sense? So if you do that, and you rearrange everything, let's see what we end up with for absolute value delta X. We'll do the math. So, right. Yeah, all three terms are negative, right? So I just throw those negatives. So 1790. Oops. Okay. This was 7291.2. That's why I'm getting a weird value here. Okay, it's because I put the wrong value in. Okay, there we go. Sorry about that. That's what I get for having to erase my board earlier. All right. There we go. Okay, and so I get a value of 6.166. I'm going to round up. So like 6.166 meters. Now it's just around 6.17 meters. Okay. Okay. And that's the depth that she goes with the water. All right. So that's it. Okay. So that's that problem solved. Like I said, I think it's you gotta be really careful with your signs here. It's kind of tricky. What's interesting is I wonder if we had done this problem a little differently. What if we had chosen to call the height at the bottom here height 0. And then maybe just giving this a variable name like this, delta x, and then solve that way. I think that might have been an interesting way of solving the calculation. And it might have, that would have made like all of our heights be positive, and I think that would have helped us get around this trickiness. We might not have had to do that. It would have made the calculations look a little weirder because our heights would have been like, 12 plus delta x for our starting height. But I think it might have been a little nicer to work with mathematically, actually. All right, well, anyway, hey, that's that problem with the diagram.